Okay, great. Our next speaker will be Yanyan, and she will talk about search for gravitational waves and its conform collapse supernova. We're looking very much forward. Thank you very much.
Thank you. Thank you, everyone. Hello, I'm Yanyan. Thank you for inviting me to your talk. Today, I'm going to talk about the gravitational wave from complex supernova. So let me give a brief introduction about complex supernova. So we know the stars are forming from nuclear nebula, and the stars have different mass. So for the very massive star, which means the mass, about 8 times of the solar mass. So the complex supernova are the very dramatic explosions at the end of their stellar life, and usually giving birth to neutron stars or black hole, or then destroy the total. So how does the explosion happen? So we know the structure of the stars. It has army-like shape, so have different elements from light to heavy. So the stars start burning from hydrogen through helium until iron. So when the iron core exceeds the transition limit mass, which is around 1.4 solar masses, the core becomes unstable and the gravity becomes the dominant force. So in this way, the core starts collapse. The inner parts then are compressed and forming into neutrons and emitting the neutrinos due to the electron capture. And meanwhile, the core then bounces, and a shock wave is launched and traveling outward. But because of the infalling material inside of the core, this shock wave stops. So in this case, we need actual energy to revive this shock. So when we get this energy, so the shock wave will be revived and keep traveling outward until it breaks the surface of the star, producing a fall explosion. So where does energy come from? We still don't have a clear answer to it. So we're writing models that will check the answer to the question, and I will talk about it later. We're super interested in the complex supernova because it's a perfect candidate for the multi-message sources. So here I show a plot. The x-axis is time relevant to a compound. So we can see in the complex supernova, it's the robust of neutrinos emitted when the core starts to collapse. And meanwhile, it also has gravitational waves emitted since the core bounce. And also the shock wave then travel outward until it breaks the surface of the star. So this time we call it shock breakout. It marks the moment that the supernova can be optically visible, which means we can detect it by our non-physical. And also complex supernova can have super energetic events. But today we are talking about the searching gravitational waves from complex supernova. I will give a very quick recap about the gravitational wave in case you remember. So of course, the gravitational wave, we can explain it in a very complicated way, it's a solution of Einstein's field equation, or we can describe it in a simple way, it's the ripple of the spacetime. We know the spacetime is curved by matter. So when the massive object moves, so it creates a ripple in the spacetime, and it propagates outward at the speed of light. So this is the gravitational wave. So as you can see here, this is we can see black hole, then merge into a big black hole. So you can see the spacetime is tilted around it. And the gravitational wave can travel at the speed of light. Around the Earth, we can detect the gravitational wave with the ground-based detector. It's created by the modified mechanism interferometer like this. And 2015, so we made a first detection of gravitational waves. It comes from one pair of black holes and merging into a big black hole. So this is the rule form how it looks like. It looks like a chart. So this is the history of the detection of gravitational waves. To detect the gravitational wave from complex supernova, you might curious how does the waveform itself look like. So far, we haven't detected any gravitational wave from supernova yet, but from a variety of the simulation, we can roughly have an idea about what we expect. So as we said, we are still not totally sure what triggered the explosion. So there are different models. For example, for the non-rotating star, or the star rotates very slowly. So people believe it should emit the neutrino, hit the meter, and revive the shortly. So here I put one spectrogram for the gravitational wave from this kind of model. You can see the frequency. The peak frequency can be very high, much higher than the unregulated modular. And it lasts for a few hundred of milliseconds, less than 100. And so if the star rotates very fast, then people believe it might be the magnetic force trigger the explosion. I also show the waveform from this model. So after this model, just to let you have an idea about how the gravitational waves from supernova look like from simulation. So even though supernova are super energetic, but the energy for the gravitational waves from supernova is very big. So we can, with our current detector, we can only detect the gravitational waves from supernova in our galaxy. So the last notable supernova in the system of the Milky Way was observed on 1987. So it is a picture of the remnants of the supernova. And as we said, we can only expect to detect the gravitational waves from a galactic supernova. So for galactic supernova, this rate is 1 or 2 per century. So it's very low. Okay, next, the background, we can talk about the detection. So as I mentioned, to detect the gravitational waves, we have the ground-based detectors. So this is the several ground-based detectors that have L shape. So we have one pair of detectors in US, and we have one in Italy and one in Japan. Since 2015, we have already conducted 4 observing rounds. The first one is still ongoing, and it will end the next year. So in this 4 observing round, we have already detected a lot of gravitational waves from binary black hole modules, black hole neutron star modules, neutron star modules. So inside the LIGO, or in the search, so they are different kind of search. So the most frequent one is the model search, which is the one we have in our detection, because the waveform for the binary black hole module, we already know them, so we can build a tensor bank, then we can do the mesh filter. But for the supernova search, we cannot do it. First, we don't have too many supernova waveforms because the simulation for supernova is very expensive, and also we don't fully understand the explosion yet. So for the complex supernova, we do the unmodeled packet search, which means we get external triggers from other telescopes. So let's say we know there is one supernova exploded somewhere at what time. So we can roughly limit the location and the time window with research. Okay. This is a walkthrough about how we do the searches inside the LIGO supernova group. So once a supernova exploded, yes, we can collect the supernova information from different telescopes, so we can just go their location at that time. Then we decide the on-source window, which is the time window that the gravitational waves method. Then we take the data inside this time window and run our search pipeline called the wave force. Then we look at if there's any triggers or if there's any possible event inside of this time window and in the search result. If not, then we can also do other analysis of them to quantify the detection range, to set constraint on the energy or the luminosity or supernova, these kind of things. This is a basic workflow. Next, I will show some results from the third observing run followed based on this workflow. So in the third observing run, so we collected 8 supernova candidates. This shows the scale location and the distance, how far away it is from the Earth. So we are trying to find the gravitational waves emitted from these candidates. And first thing, we try to construct a search window, which is called on-the window. So this is the search window for each supernova candidate. The blue and the red color indicates the data taken from 2 LIGO detectors. So you can see how the data look like inside the time window. And next, we run our search pipeline on this data. Here is what we found. So, but before introducing the results, I need to introduce 2 concepts, which is false alarm rate or false alarm probability. Because the LIGO detector is very, very sensitive, so which means that a lot of noise. Even though LIGO install a lot of sensors try to remove this noise, but we cannot remove all this noise. So that we have the false alarm rate, which means how frequently that an event induced by noise are misidentified as the gravitational wave event. So with this false alarm rate, we can estimate how noisy our research background. And we can also compute the false alarm probability, which means the probability that the false event can be identified as the gravitational wave event. So now we can see this table. So this is for search results for different supernova candidates. We have the false alarm rate and false alarm probability. So you can see all the false alarm probability are very high, except this supernova 2020 QA. So the false alarm probability is 0.05, which means it's low enough that need more investigation. So we did a further investigation. Yes, so we plotted the time frequency map with how it looks like. And we investigated the quality, what happens on the search time. So the conclusion is this event is very likely induced by noise. So far, which means instead of observing around, there's no gravitational wave identified. Even though there's no, we didn't find any gravitational wave, but we can still do some analysis. For example, we can take the wave forms from different simulations and estimate the detection range, which means up to which distance we can detect this supernova signal. So here I show you focal graph. So that is detection efficiency, and the y-axis is distance. And these different colored curves indicate different waveforms from different supernova simulations. So the conclusion is for neutrino-driven explosions, this distance can be up to 8.85 kilopascal. And for the MHD model, the distance can be up to 10 kilopascal. We also have a tune emission model, which means if the progenitors start rotating very fast, so they must be produce some lumbar model instability. So for this kind of models, this distance can be up to several megapascal. Okay, this is what we did in 03. So in photon searches, which is ongoing, so we have already collected around 23 supernova candidates. So up to 20 megapascal. And one very interesting supernova candidate is supernova 2023 IXI. So it was exploded last year. And the distance is 6.7 megaparsec. This is one of the closest supernova exploded in the last decades. So the search result, we already have the search result, and it will be released hopefully very soon. So because it needs to go through some legal procedure, so other the results, hopefully we can release it next month or this month. And also take a picture about the supernova. And if you notice the background of my title page, this is also the background of my title page, this supernova. Okay, I think that's what I would like to share with you today. Thank you.
Very much, Yanyan, for the nice talk. We have questions. Do you have questions from the audience?
In terms of 2020 FQD, can you actually take some waveform and do model search to magnify the signal to noise?
Okay, so you need to do model research.
Yeah.
Yes, we can do it. Actually, several groups are working on it. But the one issue when we call doing model research is we might not have enough for supernova waveforms to do model research. Yeah, so which means the results might be a little bit it's better to have more waveforms, but definitely we can do it. The model research it works just around measure filter.
2.7 signal is kind of interesting.
Yeah.
Looks small.
Another question.
I don't have a question, but a very short comment.
And
Just to close the circle,
Mhm.
for the explosion mechanism in supernova, turbulence is essential, right? Without turbulence, they are not going to explode.
maybe.
Cluster attack.
Huh?
The cluster attack. It's not a-
Yeah. Maybe.
Further question, please.
I'm just confused about one thing. So, you first detect the supernova events and then you look for the gravitational wave signal. Okay.
Yeah, so the supernova, when a supernova is exploded, there are other observations that can detect it, right? So they can tell us when they detected, when it was discovered, for example, this supernova, it was discovered on May 19th. Then based on the discovery time and also their previous observed data, so we can roughly quantify the time window that the explosion time will run, and also the time window that the supernova signal, a gravitational signal might occur. So that's why we call it optical trigger research.
Any other question? Okay, if this is not the case, let's thank Yanyan. Thank you to all of our three speakers today.